Welcome to signal processing for millimeter wave in 5G and beyond. We have learned so far some of the characteristic of the digital channels. Today we will be covering the lecture number 10 of the module 2. The kind of topics that we will try to cover here are the following: delay spread of the channel and how it appears from analog to digital, and what exactly the modification happens from RF analog to digital, we will be showing in details. Then the definition of coherence bandwidth of channel, very important parameter, and then we will touch upon, probably we will discuss this aspect, the third aspect in later lectures, but it will be just an introduction of the frequency dependency on channel taps. Now we will be learning more into that, some of the parameters that impact the channel performance. So, we have learned in the last class the frequency flat fading channel, frequency selective channel. Now, we will learn more on that. So, we are talking about the bandwidth. One is a frequency flat fading channel, frequency selective channel. So, if it is a frequency selective channel, say frequency selective channel, what is the bandwidth? I do not know, but at least I can guess BH will be less than your BS, that much I can know. We can't say specifically what should be the bandwidth, but I know for sure it is less than my transmission bandwidth, obviously. That is the reason it cut down some of the frequency component of my BS, and it creates the time domain aliasing, okay, or time domain interference, ISI. If it is a frequency flat fading, channel, what will be the case? BH will be BS, and you will have just one tap, you will not have multiple taps. If I have more than one tap, obviously it creates distortion. So, frequency flat fading, except the amplitude distortion, overall it does not discard any of the frequency component present in the BS, but there will be amplitude distortion, obviously because it is a filter. Then we phase distortion, obviously because it is a filter. Okay, so this is what we have learned. Now, what is the bandwidth of it? So, now let us concentrate on the bandwidth component. So, can I quantify this bandwidth? Obviously, because it is a HZ, it is a channel. It has you know all the coefficients. So, can I know its bandwidth? Of course, you know it. How? You will have all your HL e to the power minus j omega L, L is equal to 0 to capital L minus 1. So, this whole equation is given. If the equation is given for a FIR filter, it is not easy to, it is not difficult to get a channel bandwidth. You just replace z is equal to e to the power j omega and done deal. You can plot the whole thing and see what is the bandwidth coming. Okay, that is one part. So, if I know HL, I know the bandwidth. So, the question that comes, does it have any correlation with the does it have any correlation with my delay spread? Okay. Now, there are two ways you can formulate it. One is that there is a maximum delay spread that we have already defined it, and there is also an RMS value of delay spread. Okay, that is the way we define the RMS value, but RMS value I am not talking of right now here, I will be talking next. But here I am just defining the kind of expected value of my delay spread and see, can I relate my bandwidth with the original channel bandwidth. Now, the question that happens is that this HZ is a digital version of your channel, right, after the ADC sampling rate, but this channel inherently is coming from the analog and RF, that also has a bandwidth. What was that bandwidth? If you remember, let us say this is analog or RF, what it was? It was summation of alpha I b, b happens if it is an analog, if it is RF it will be just alpha, because it becomes a complex number due to the delay. then e to the power minus j 2 pi, this is the one, right. Remember, this is the one for the bandwidth case. Now, the question is that from here also this is a transfer function for the RF and analog case, and this is the transfer function for the digital case. Do they produce the same bandwidth? Logically, yes, they have to, because it is the same signal, I just digitize it. The bandwidth doesn't increase or decrease. Okay. Due to my sampling rate, the bandwidth can be corrupted some of the thing, because I may see some sort of an aliasing. That can happen, but bandwidth cannot increase it, right. You cannot have a more extra component just because you have done some sampling, that does not matter, that does not happen. So, tentatively the bandwidth from the digital side and from the analog side would remain constant, that will not change. It may be degraded here. Why? Because I may do a sampling where the analog bandwidth can be degraded. Why it can happen? It depends on sampling, right. Suppose this channel, this analog wise or RF wise, it gives us a 5 megahertz bandwidth. So, to reconstruct the signal, I need to sample at 10 megahertz, but at the receiver I do not know what point I need to sample it, right, because I do not know the channel bandwidth. So, I may sample at either high, where it is okay, I will not see any sort of degradation of bandwidth, or if I do not know, I may sample at even at lower frequency, right. Say instead of 5 megahertz, 10 megahertz IQ rate, I may sample at 8 megahertz. What does it mean? I will see a 2 megahertz aliasing. So, effectively it reduces my bandwidth, because aliasing is just killing the part. So, it all depends, but at no point of time I will see a larger bandwidth of it, right. That cannot happen, I cannot create that extra bandwidth, but I may either maintain it or I can degrade it. So, the point here is that can I guess the bandwidth? Okay. Can I guess the bandwidth? And the good news is that I can guess the bandwidth. So, if you know your tau d is your is the delay spread, analog delay spread. So, it can be shown, or it can be experimentally you can show that this one almost equal to, I have not written the same thing, I have not written equal to, it will be, rather I will put it this way, the bandwidth of the channel this is the case. Tentatively we can have some assignments, obviously we will have some assignment where we will show that the bandwidth here whatever comes is very tentatively equal to 1 by 2 of tau d. Okay. But it makes some assumptions. The assumption here is that every tap values in the RF will be almost equal. So, it is as if like some sort of a pulse impulse kind of things. Okay. So, those kind of basic assumption, but it works tentatively, it comes into picture. Okay. Now, let us move on. So, this is just kind of a tentative, I can't say that this is exactly equal, because it has certain character, it has certain assumptions. So, what is the assumption here? Assumption here is that if you have a tau, say tau 1, tau 2, say tau 3, all of them will be almost kind of equal. So, it is as if like a sync pulse of width tau d. Okay. So, what is the bandwidth of such kind of sync pulse? 1 by tau d. So, if I just say I take frequency domain of it. So, what is it is 1 by tau d, right. That is precisely what it means. So, here it should be BH, it is BH. So, effectively my BH should have been 1 by tau d, right. So, but there is a half here, okay. I have reduced it just because I take the 3 dB point here. So, if I do not consider this point as my bandwidth point, that is the point where it is making 0, I just make a 3 dB. So, what is that? The power should be just, I just make it slightly up. So, instead of the complete tau d, I just consider a half of it. So, that is why this 2 part comes into picture. So, this is my effective bandwidth. It's not a, there is no proof on that, but this is more of an intuitive engineering kind of solution. There is also a relationship between the bandwidth as well as with its RMS value of it. We will explain it later. What is RMS value of tau d? So, this tau d is more of an instantaneous tau d. There could be an expected value also, we will explain it now. So, we will come to that point later, but this is the basic logic here. So, tentatively it is as if like one impulse response in tau. So, when I do a impulse response in the frequency domain, it just becomes a sink. So, the point where it is 0, it is 1 by tau d, and that is basically we consider it as our bandwidth. But to be conservative, what it does is that it takes 50% of the time and say that that is what my bandwidth is. So, this is one definition of the bandwidth, but this is not this is not a very theoretical way of thinking it. This is more of an engineering way of thinking it. Okay. Now, there is one more point here. The bandwidth I have just shown you, it is an instantaneous, whether it goes through RMS value of it or it goes through direct instantaneous value of it, but this is more of an instantaneous bandwidth. Okay. But as you know, your physical system can be a random system, right. So, now you are so far I have assumed static, now we will moving slowly to the time domain cases. Slowly we have assumed so far we have assumed the static system. So, what does it mean? Nothing moves out, everything is just constant. But let us take a different snapshot, though it is constant, let us not assume that things are moving continuous in time. Let us take different snapshot. For example, I am taking a snapshot at say 7 a.m. I want to know what my channel is, it is a snapshot. Then I say I am taking a snapshot at 7:05 a.m. after 5 minutes, I am taking another snapshot. Snapshot meaning I just transmit and see what my channel is. And 8 a.m. I am taking different snapshot. So, practically the channel will vary because it is not physically constant. So far we have assumed static, but practically it will not be constant, right. So, that means at 7 a.m. some channel will be there, at 7:05 a different channel will be there, because something would have moved, you may have moved, something would have moved, but I am still not considering a continuous time movement. It is just like you are taking a discrete snapshot and taking a different channel. How do they move? At 7 a.m. you can't guess at 8 a.m. how the movement will be, right. So, I can say at any snapshot my channels are kind of a random variables, right, because you do not know the position of the reflectors and scatterer. So, what does it translate to? The tau d itself will be a random variable, itself will be a random variable. That means at whatever time sample you take it, the tau d, the delay spread would be a random variable. What does it translate to? The bandwidth of your channel BH, whatever we have discussed so far, that would also be a random variable naturally. So, that means there is no instantaneous bandwidth that we are talking of. I would say rather it is some sort of a expected value, some expected, this is a random variable, this is also a random variable. So, the bandwidth that I am talking essentially is more of a expected value, or on an average what is the bandwidth that system gives you. Okay. So, what does it mean? It is not equal, but tentatively expected value of 1 by 2 into tau d, that will be coming into picture. See, if this is a random variable, obviously the expected value of this one will be giving expected value of bandwidth. So, this is an important result. For example, I give you a simple task, you can try it at your home. Say tau d, it just takes some distribution, let us say it is an exponential distribution. This is the PDF. PDF of it. Can I find out E of BH? You can. I am just giving you a hint, you can try it at your end. So, what do I need? I need to know what is the expected value of my bandwidth that comes. So, that is an expected value, because there is a randomness here. So, what is that? Is 1 by 2 into tau d, okay, the PDF of tau d. So, it should be P of tau d integral d of tau d, that will be coming into picture. Okay. So, what is the limit of your integration? Tau d is a delay, right. So, delay cannot be negative. So, 0 to it should be infinite, of course, because you do not know where things are. So, it will be 0 to infinite lambda e to the power minus lambda into tau d half 1 by tau d. I am not solving that problem, solve it, you get some sort of a bandwidth concept. So, these are these are all computer simulated issues, because it is not so easy to get the exact distribution of tau d, and also sometimes it becomes very complex, but it is a simple case that I have assumed here, because the distribution of this tau d is not so simple, it will be extremely complex. In fact, if you look at the way the random variable is constructed, if you look at the way it is constructed, okay, it is I do not know where it is. The tau d defined as max of tau I minus tau j. So, basically it is kind of an ordered statistics. It is tough to get the exact distribution of tau d. Okay. Suppose you have 20 such reflector and scatterer, and each and every reflector and scatterer has a say Poisson distributedly movement. It is virtually impossible to find out this one. Okay. So, this can be done only in a computer kind of big simulation, and you can try to get the distribution. Okay, but this is just a simple problem where you have just only 2 of them, and I am telling you this is the distribution, you can find out the bandwidth. Okay. So, now our key result is done. So, key result is this, the bandwidth is expected value of 1 by 2 of tau d. So, this is an important result. Now, this bandwidth, the channel bandwidth, has a very interesting name, it has a technical name. Okay. So, this BH or the bandwidth of your channel is also called coherence bandwidth. Coherence bandwidth of the system of channel, you can say coherence bandwidth. It is a very typical name that is there in 5G, 4G, everywhere, coherence bandwidth. So, it is nothing but the bandwidth of your channel. Okay. Okay. So, what is the best way to find it? Well, you get the channel, you get all the Hz. If you are not getting into the delay spread way of calculating the channel bandwidth, that is absolutely fine. You get the channel taps, all your H0, H1, blah blah, HL minus, estimate it, construct an FIR filter, then you get a bandwidth. This is the best way to get the bandwidth. Okay. So, that will be your coherence bandwidth, and that is the easy way to get it. If you know what is the delay spread, and expected value of 1 by 2 delay spread will be your channel bandwidth. Okay. Now, so far we have covered the channel in a static environment. Okay. Now, before I get into the time domain variation of it, I would now like to have a more characteristics on the magnitude part of the channel. So far we have not done much, that means the characteristic of that alpha b, this part, the one which is like the attenuation part. It is a complex number, that is the only thing we have known, but is there anything else? Because why I need to know? Because that drives the millimeter wave and terahertz kind of communication, because this component is the key focus. Once your system bandwidth becomes larger, once your RF becomes larger, so because we are moving towards that millimeter wave, right. So, it is very important to know what the exact characteristic of it. Okay. So, let us try to understand it. Okay. After that, we will definitely come back again for the time varying part. which will be the next part of our lectures. So, we are now characterizing the alpha part, the attenuation part of my channel. When I say attenuation, does not mean that it will be only the AR part, right? I mean, you have explained multiple times. It will be everything, LNA, power amplifier, all DAC, ADCs, filter characteristic, everything all composite is your channel. Okay. But here we are only characterizing part of only characterizing the AR part, because AR is something that which you may not know, only thing you have to do a measurement and kind of. So, AR part only you are trying to characterize it here. So, so far we have not concentrated much on the on that aspect. So, now this is just a single antenna to single antenna system. Let us concentrate on that only. So, when I transmit the data here, it will be received here, and we do not want to get into the electromagnetic waves definition. We want to go everything into the electrical domains, okay, electrical engineering domains here. So, that means I send an electrical signal, I receive an electrical signal. That is my way of viewing the channel. I do not get into the electromagnetic business here. So, here so the gain part alpha that we defined last time, we said that that is nothing but the path gain, right, path loss you can say, but as because there is an LNA here, it will be so just a path gain, this alpha, and the complex part is coming because of the delay part. So, if when I say alpha, I am talking of only the RF part, because RF to analog it will be just the e to the power minus j 2 pi f tau I, the complex part will be added. What exactly this alpha? The one which you have explained so far, that is defined by a path loss equation, right. We know the path loss equation in a free space. So, that is defined by your Frisch equation. Right. So, what was that path gain? We have I think tentatively defined it. It was dt into dr into lambda by 4 pi f. 4 pi r if the distance is r. Okay. But so, this lambda makes it kind of a frequency dependent. So, I can say this part is some sort of a function of say let us call it G1 f, just an functional assumption. So, let us call this whole thing as G1 f. Why is f? Why f is coming? Because there is a lambda here, right, and and there is the relationship between lambda and frequency, right. So, lambda into your f, that will be your c. So, that part is there. So, let us call it G1 f. Okay. So, that is there. C is the speed of light. Okay. So, that means this alpha is predominantly we have already accepted, and we have well defined how it can be frequency dependent. Now, this component only assumes that you are in a free space, because this Frisch equation is only for free space. But we are in the world practical system, and the next component. So, this is fine when you are in a 6 gigahertz kind of transmission, that is typically your 4G system works 6 gigahertz. 5G also some of the components work in the 6G, but when you increase your RF say 30 gigahertz, 40 gigahertz, 60, 100 gigahertz and so on beyond, free space part is not the only component that is affecting your alpha. More and more other part will now come into picture. Okay? Let us understand that. So, this alpha so far it was G1 f, that particular gain, that was from the Frisch. Apart from that, it also has one more component called absorption. Why this absorption is coming into picture? Because we are now getting into slightly millimeter wave, though it is not the complete definition of millimeter wave, just the warm up how millimeter wave impact my channel, what exactly it is meant by a millimeter wave channel. So, before I get into it, this alpha definition has to be very thought through. So, there is one more component called absorption. Why this absorption is coming? Because when you transmit the data, it goes through the medium, right. Say for example, when I transmit, it goes through air. Air is a medium. So, air will have lot of components. So, for example, carbon dioxide, oxygen, sulfur dioxide, water vapor, so many other invisible or some sort of a visible components like color. So, all these components will act as an absorber for the RF. So far, that was not a concern for us, but moment I get into say 30, 40 gigahertz RF and beyond, the absorption part becomes predominant. It not just the free space that deteriorates the gain. Absorption will now be coming big way. Okay. So, now there is a there are different model of absorption. One of the key model of absorption is that it is basically called, so let us call that as a G2 of F, this absorption part. So, this will be e to the power minus half of I will define it what is something like that. What is Kf? Kf has a well definition. I am not going into details of it, because that is not the intention of this particular lectures, because we are more in the signal processing aspect. So, this is more from the physics aspect. So, this is basically your absorption coefficient, which is a function of frequencies, and that also depends on materials. If it is a water vapor, it will have some Kf. If it is some sort of a other materials, like for example, wood or glass or anything, any materials, everybody has its own absorption, then everybody will now start absorbing some of the data, some of the power. So, that means if an RF of say 30 or 60 gigahertz goes into the air, various component of the air like water or carbon dioxide or oxygen, whatever, you will start doing a different level of absorptions. Okay. So, and this Kf can vary, it can be multiple such things will be there, and R is the distance. So, that means depending on the R, obviously your absorption will be larger and larger. So, this Kf has a very complicated definition, I am not getting into that. The reference paper that I have shown, or I will also show you at the end of the lecture, it will have that paper and it will have a very big definition. So, let us not get into that, but here it is more of a notion what exactly it is happening. Okay. So, that means this alpha is now G1f, which is the frisch part, G2f, which is basically your your absorption part. Apart from that, there is one more part, okay, and that part is called phenomena dependent. Phenomenon. What is the phenomenon? What are the different phenomena that happens when a ray is injected into the air? You have reflection, you have scattering, and you have diffraction. These are the three phenomena that happens, okay? And each and every phenomenon will create a different physical activities on the array that comes into it, incident onto it, right. Reflection is just a reflection, scattering is like a splashing, diffraction will slightly bend it and try to deviate the ray from the original direction. So, that creates that has a frequency dependency. That means 6 gigahertz will see a different type of reflection compared to 60 gigahertz. Okay, that is again it is done by a physics. So, the reason is that a surface, the level of absorptions from the surface, the level of scattering from this surface will be dependent on the frequency. Why? Because the lambda will see a different level of roughness into the surface. If the lambda is large, what will happen? A rough surface will become like a smooth surface, but when the lambda is smaller, that is precisely when you are millimeter wave, 60 gigahertz millimeter wave. Each and every tiny things in the system, even a glass kind of things also, it may look like a scatterer, because it may see that roughness there. Okay. So, depending on what frequency you are transmitting, these phenomena will be slightly varying in their nature. So, there is a coefficient called RF. It comes from reflection, scattering and diffraction. Again, I am not getting into the details of this equation, because again that is not the part of this discussion here. So, this alpha, whatever gain factor we were talking, it will be that G1 of f, which is the plane frisch, just the path loss, multiplied by G2s, G2f, which is the plane absorption part, and multiplied by the phenomena related part. So, these three things defines what should be my alpha. Okay. So, today we end this, we will explain more on the next class. Okay. So, this is the reference, Fundamental of Wireless Communication by David C. and P. Viswanathan. This does not cover everything, but most of the things you may find it. Thank you.